So, since 1992, when this first planet was discovered, we've of course been out looking around all the pulsars, and we're very good with these pulsar measurements of making very precise measurements. We're not going to miss many planets, but funny enough, we haven't really been able to find too many, but we have found a couple.
Here's one that was discovered. It's around the pulsar B1620-26. And this pulsar is a bit different from the one we've been talking about so far because it's not in our own galaxy, but in the globular cluster M4, the SEA4, which orbits around. And this is an incredibly dense environment of close-packed, very old stars.
So there's about 1 million stars packed into this little, fuzzy ball of that we see up in the sky with your eyes.
And it turns out this is actually rather a different system from the first one we talked about. What we have is a neutron star, and this one does have a white dwarf orbiting it, just like you predict. And then the planet is further out. So the planet is actually orbiting around this binary neutron star and white dwarf. So how do you form something like this? Well, the current theory about how you form this one is it relies on the very dense environment of the globular cluster. Where we are in the galaxy, stars almost never come near other stars. There's just too much space between them. But in the middle of a globular cluster, stars do have close encounters with other stars quite a lot. So here's our current bet about what's happening. We started off with a planet orbiting a main sequence star, much like the Earth, around the Sun. And we had a white dwarf and a neutron star. And they came close to each other and got a bit muddled up. And the net result was, after they all jiggled around and did their dance, is the white dwarf went off by itself, leaving the neutron star orbiting around the normal main sequence sun with a planet left in the outskirts. And then at some later stage, the main sequence star swelled up, spun up the neutron star into a millisecond pulsar and then turned into a white dwarf itself.
It's almost like a human relationship here, I guess, where we end up with a sort of a new family after the fact.
This seems to work. You can do the numbers, and it looks like it's a reasonably plausible thing to happen. The main interest in this is that in globular clusters there are very few heavy elements. So people thought the planets are made of heavy elements, and there shouldn't be very many planets here. So the fact that we've seen a planet in this environment with very low heavy elements is actually quite interesting. The second thing is this globular cluster is extremely old, over 12 billion years old. So that's telling us that at least some planets were capable of forming around normal stars when the universe was very, very young, which you might not have expected.
So this is an unusual system. Maybe we should look at one which is similar to the first one. Have we found anything like that?
Well, this is the closest one. It's only discovered quite recently by Australian astronomer Matthew Bales and his team. J1719 minus 1438. These are the coordinates on the sky.
They could come up with better names.
They could indeed. Well, this one, in fact, is generally known as the Diamond Planet.
Ah, that is a good name.
Yes. So what we've got here is, here's the motion, and it's oscillating in velocity by about the same amount as the first one we saw, so about a millisecond. You can see we have exquisite precision.
And it's nice. It looks like a single sine wave this time.
Yep. This is what you'd expect from a binary. They have a second star, except the amplitude is much too small. So this thing that's orbiting around it doesn't have the mass of a neutron star or a white dwarf. It has the mass about that of Jupiter.
Okay.
But this is going around every 2.2 hours. Now, the Earth goes around the Sun once a year. This goes around in 2 hours. So its year is 10 times smaller than our day.
Wow.
It must be incredibly close in. In our own solar system, it would actually be inside the Sun to go that close in. But luckily, a neutron star is much smaller, so it can actually be outside it and going around that fast.
So this would be quite an interesting place to be because, you have the whole mass, or 1.5 times the mass of the Sun, crammed down into this tiny thing 10 kilometers across.
This is much too big to scale.
And then you have a planet orbiting it right next to it. So that is going to give you some interesting forces compared to what we're used to here on Earth.
You can do the calculations. What you find is, of course, if it was something, we know it's got about the mass of Jupiter. We don't actually know its the shape or colour or composition of Jupiter. But if it was, and every planet we know with that mass so far is a gas giant,
Yep.
the nearest bit is going to be much closer to the neutron star than the further bit, which means gravity here will be much stronger than gravity over there. Now remember, to stay in orbit, centrifugal force must balance gravity. Because gravity is much stronger here, this bit must be orbiting much faster than that bit. That's not good. If you had a planet and the near side of the planet is orbiting 10 times faster than the outer side of the planet, that's not a planet anymore. It's been ripped to pieces.
Yeah, so it's going to be ripped to pieces by these effectively tidal forces.
So how can it be there? Well, the only possibility is if it's not this big, if we make it much smaller, that means that the distances are more similar, so the gravity is not going to be so different. Also, it's going to have much stronger gravity, so maybe it's got enough gravity to hold itself together. And so you can calculate a sort of minimum density, a maximum size for this thing. It turns out to be absolutely tiny. What you need is something like this.
Ah, so imagine that you go through and, the heaviest thing we could make it out of, if it was, we could make an osmium planet that has a density 22 times of water. That's the heaviest element there is. But this thing is even denser than that.
Well, 22 times would probably do it, so it could be an osmium planet.
An osmium, well, okay, it's pretty crazy to do an osmium
But that's hard
planet,
to imagine.
But it may be more likely for it to be formed from the star that spun the planet up.
Remember, this is a millisecond pulsar, so once again we've got the problem, where did the star come from? So maybe this very dense Jupiter mass thing is actually the remains of that star. So possibly it was a white dwarf and it fed the matter, spun this up, and then we had the black widow phenomenon. The X-rays, as the matter fell down, it produced X-rays, these came out and zapped the star and blew most of it away. And all we're left is the core.
So if you think of what the core of a dead star, a white dwarf is, well, the sun, for example, when it is becoming a white dwarf, is going to be making helium into carbon. And a little bit of oxygen happens on the outside, but inside it's effectively forming carbon. And so the core of a white dwarf we expect to be carbon. And as this carbon initially is very hot when the sun becomes a white dwarf, but over billions of years it can cool off, and it becomes this giant carbon crystal. And we know what carbon crystals are. Those are diamonds. So this really could be a diamond planet.
It wouldn't actually be a shape like this, it would be a spherical, but it would be made of diamonds or maybe even some other form of carbon, even more compressed in the middle. So this is the idea that we might be talking about a diamond planet here. So that's what we've learnt so far. We've now found 3 planets around pulsars, and they're all weird and wonderful in their own way.
Yes, but it's not exactly where I would be expecting to look for life.